So this is where the good stuff begins. So I will be speaking about thin lenses, and we will be unraveling to you how we can understand how they can be used to image objects into image location points. So this is what I will be speaking about, and I will just straight on go into the actual business. So I will be start by going and speaking about how we can understand spherical lenses. And essentially in the previous lecture, we understood how a single spherical interface behaves, and now we are just combining those two spherical interfaces together to resemble something looking like a lens as shown in the figure. So we take the refractive indices of the lens again to be a constant valued. Here we denote that with NL as in lens, and then the refractive index profile of the surrounding medium to be NM as in surrounding medium. And most of the time when we actually do calculations, we can take the surrounding medium to be air, so NM is most of the time just unity. And the thickness of the lens, let's assume that is D as shown in the figure in the middle part of the figure. And now we can write equations for the two interfaces of interest. And this was the equation we just derived in the previous lecture. So we can apply that for the first interface on the left-hand side. So that would be then now NM divided by SO1. And please note that another label here with the first interface, I'm denoting this with the sublabel of 1. And then if I would have the second interface, I'm denoting the consequent parameters with the index 2. So, and then the second term in the equation will be NL divided by SI1, and then this is equal to the NL minus NM divided with the radius of curvature R1, and then we can write the same kind of equation for the second interface, now NL divided by SO2 plus NM divided by SI2, and this equals to NM minus NL divided by R2, so the radius of curvature of the second lens. So this would be the radius of curvature of the second interface. Sorry, and I think I said lens in the previous previous sentence, and this would be the radius of curvature of the first interface. So this would be the R1, and the other parameters are shown here. So the SO1s, SI1s, and so forth. So we can now combine these into a single equation. We can just merge them together, and what we have is that then we have NM divided by SO1. We have NL divided by SI1 plus NL divided by D minus SI, and then we have NM divided by SI2, and this equals NL minus NM, and then this is multiplying R over 1 over R1 minus 1 over R2. And that's it. So we basically just combine these equations together. We can mindlessly multiply them together, and we get a single equation that gives us the kind of what happens for a ray of light propagating through the lens. And this, we assume further that we are dealing with a object that we call a thin lens, and this is another assumption or approximation to make. And what this means is that we are considering lenses that we have the thickness parameter D that is very small compared to the other distances, essentially to the object and image locations and the radius of curvature. And in this case, we can simplify the equation, so we can get rid of the D parameter there, the thickness of the lens, and now we only have this kind of equation at hand. So this is now that we can use already. And now this is a special case how we can approximate things, that this is a very, very common case. We can assume that this lens of ours is actually surrounded by air, so that the NM equals to unity. And in this case, the equation that we have derived now is known as the Lensmaker equation. And here, the kind of inverse of the backfocal length of this kind of lens would be now given by simply NL divided by NM, and then the NM would be unity. And minus 1, and then we have the differences of the inverses of the radius of curvature. So this would be what we would have at hand. Lensmaker equation is this guy, and we just equate NM to be equal to 1, and then this would be known, this equation, as the Lensmaker equation. So it's not actually this one. I was so too hasty here. So now what we are calculating is that we want to calculate the inverse of the backfocal plane. And then we can just solve that from this equation by just using the same formalism we did for a single interface. so that we take our rays that are propagating along the optical axis before they hit the lens. So we first consider that our object is at infinity, and then we put infinity here, so we get 0 out of this term, and then we have 1 over SI2 here, and then this SI2 corresponds to the inverse of focal length here. And that way we get this equality. So we are just considering the case, what happens for rays of light that are coming along the optical axis. This black line here is again our optical axis, and then where they will be focusing down here somewhere. And that's the way how do we calculate what is the back focal length. And then we can do the same thing for the front focal length FO. And now we are considering, we want to calculate rays that after propagating through the lens, they would be propagating parallel to the optical axis. And now we want to see where would be the object location where they want to originate. So essentially, where would be the front focal length or front focal plane of my simple thin lens. And this way I can use the same equation, and now what I get out is that I have the image being formed at infinity, so SI2 will be infinity. So what is left is that then I only have the object location, and that I equate with the FO, so that the front focal length. And this is what I can solve. And now in our scenarios we can compare both of the equations we just derived, and we see that for the case of a thin lens, and this is of course different from the case of a single spherical interface, we see that the front focal length and the back focal length, they are actually the same. And we can just write that the front focal length of my lens, thin lens, is F. So this is what we see here at the end of this derivation. And this of course is not generally true for all kind of arbitrary lenses. This applies for the thin lenses, but if you don't have a thin lens anymore, then this won't be true anymore. And please note, in the follow-up courses, we will be also generalizing the concept of thin lens into thick lenses, so that that's also something that will be on the way if you're careful enough and progress far enough in terms of optics. So let's now look. When we are looking at the objects and the images distances, we can just denote that the object location SO, we do not need to use this kind of complicated labeling anymore. We can just denote the object's distance from the first interface with SO. So we can just write that where our object location is. We can just write this to be SO. And similarly, the image location, we do not write that to be SI2, but rather we can just write SI to kind of simplify our mathematical terminology here. So this helps out in terms of writing things down into equations. And now what we can see is that then we can really simplify our equation. And now our imaging equation becomes to 1 over SO plus 1 over SI equals 1 over F. And this is super nice. This is actually known as the thin lens equation, and here the inverse of F is also known as AD parameter, which is also known as the lens power, and this is known as the Gaussian form of the thin lens equation. So this is super nice. We have a simple equation that gives us a means to understand how light is being propagating through, how an object point is being imaged once we know what is the focal plane of my lens. So this is super nice equation. And looking at the Lensmakers equations that we just discovered in the previous slides, we can even calculate the inverse of the focal point, 1 over F, that it's NL divided by NM minus 1, and it's also the 1 over R2. Sorry, 1 over R1 minus 1 over R2. So we can even see by looking at this equation that we can even control quite easily what is the actual focal plane of my lens. So I can definitely control the refractive index profile of my lens, and even more importantly, if I control the radius of curvature of the two interfaces, I can control the front focal plane quite nicely. And this is quite important. I can control the radius of curvature of both interfaces in order to adjust the focal plane of my lens. So we see, for example, that if we have the refractive index of the lens NL, that if you change that, the power of the lens is being affected. This is usually not the strongest of ways how do we modify the refractive index profile. Rather more usual is the case that we are actually changing the radius of curvature. And the bit of terminology here, that if we have a convex lens, essentially that means that the focal plane is positive number as shown in the figure A. That's essentially how a convex lens behaves. It focus light down into a kind of one spot. And then we have another possibility that we have a concave lens, and their concave lens is being defined such that the focal point F or focal plane F is, or focal length F is smaller than unity. And that's shown in the, sorry, not unity, but smaller than 0, a negative number. And that's shown basically how it behaves in the figure B. And please note here that the kind of like is the lens convex or concave, it's really defined with respect to the focal lengths. Is it a positive or negative value, and not really necessarily like are the surfaces convex or not. Because I could, for example, have a plano convex lens, or I could have a plano concave lens, so that they like it doesn't really mean that convex lens is a lens that we have both surfaces convex, but rather it's being defined with respect to the focal lengths and not with respect to the radius of curvature. So please note this. So convex lens, what it does, it focuses light, incident rays of light into a single focus point. And when especially the rays of light are such that they are propagating parallel to the optical axis when they are hitting the lens, where they are being focused down is that they are being focused at the back focal point Fi. So basically they propagate through the point Fi, and this is how a convex lens can be thought to behave, like shown in the A figure here. And then let's consider a concave lens. In a way it behaves similarly, but now when the incident light propagate parallel to the optical axis, they diverge after they have propagated through the lens, and now they seem to originate from the point of the front focal point Fi, as shown in the figure. And now in the kind of terminology of real versus virtual image, we would see that this is actually a virtual image point that would be formed into the front focal point here. So the rays of light actually do travel along this path, the solid line here, and this is where they actually will be propagating. But when we would be looking at the rays of light in here, it would seem that they would originate from this point, and that the image would be here. So that's why this would be a virtual image location. So the rays actually do not cross here, but they seem to be crossing there when we are looking at them from here. So this is the difference between a real image point and a virtual image point. Please note the difference here. And if you have an ideal lens, it doesn't really matter at which angles the rays of light are incident on the lens. So this is the kind of outcome of the paraxial approximation we make. And this is what we should remember here. So when we have the rays of light propagating along the optical axis, they are being focused down after a distance of focal length F into the focal point Fi here. And if you would have the same kind of like a parallel bunch of rays propagating at a different angle, they would be focusing down into the same plane. And this plane would be known as the back focal plane. So this is the kind of assumption that arises because we are implicitly assuming paraxial approximation to hold here. And this means physically that it doesn't really matter at which angles the rays of light are incidents on the lens, they behave the same way. And basically back focal points Fi form a back focal plane. And similarly, the front focal points Fo form a front focal plane. But I would like to end by just mentioning that once we would go beyond the paraxial approximation, this scenario that where we have the bunch of rays propagating at a different angle, the point would not be exactly on the same plane anymore, but would be actually a little bit more, most of the time would be a little bit before here, so that the back focal plane would actually, when we go beyond the paraxial approximation, turn into a surface and slightly curved surface as such. So this is also something that we would need to generalize when we would generalize our treatment. But in this course, we are not going there, so please be happy with the notions of the back focal plane and front focal plane, and this is where the image points get formed, if the object is at infinitely far away from the lens. So this was my lecture. I hope you enjoyed, and please join me quickly in the next one when we will be speaking about image formation. So we will be looking more what happens when we are imaging using thin lenses. So thanks for listening this one, and please stay tuned. Join me quickly with the next one. Thanks and bye-bye.